Hello everyone, my name is Lokesh. Today I'll be discussing about Ozone and how Ozone today balances and deletes data at scale. A little background about me, I'm currently Senior Software Engineer in Cloudera. I hold PMC and committer privileges for Apache Ozone, Apache Ratis, and Apache Hadoop. I have been contributing to these projects for the past 4+ years. So let's start with a basic introduction about Ozone. Ozone is a distributed object store. The namespace comprises of volumes, buckets, and keys. It has accessibility using the object store file system as well as the S3 API. It started off as a sub-project in Hadoop, but currently it is a top-level project in Apache. So let's dive a little deeper into the architecture. In case you already know about the Ozone architecture, you can skip this topic. I'll also be discussing the architecture in detail, along with performance improvements in Ozone in a separate talk in SDC. So Ozone implements a Hadoop-compatible file system API, and that implementation in Ozone is called Ozone File System. So big data applications today can access Ozone using Ozone File System. So Hadoop-compatible file system API is part of Hadoop project. It has been developed and promoted by the Hadoop community. Today, most of the major big data applications and Google Cloud provider, cloud storage, or S3, Azure Data Lake Storage, all of the major cloud storages also provide their own implementation of this API. So Ozone has been designed to coexist with HDFS in the same cluster. The data nodes can share the same disk, and Ozone has been designed in a way that it does not interfere with other HDFS services. So let's look a little deeper into this, the Ozone architecture. So we have data nodes. Data nodes are the storage nodes. They comprise of multiple disks which store the file or object data. Then these data nodes are managed by Storage Container Manager in Ozone. Periodically, these data nodes would send container reports to SCM. SCM would analyze these container reports and make sure that all the containers are sufficiently replicated in the system. What that means is, in case it finds a container is under-replicated, or it does not match the required replication factor, it will schedule replication for that container. And if it finds a container is over-replicated, that will schedule a deletion for that container. SCM also maintains a container map, which is a mapping of container ID to set of data nodes containing replica for that container. Both of these components, data nodes, together with SCM, they form the HDFS or the storage layer for Ozone. So container is a collection of blocks. So container reports, what that means is in data node, the data or blocks are collected into container, and container by default is 5 GB in size. So instead of sending a report for every individual block in data node, the data node is rather sending container reports to SCM. So both of these components together form the storage layer. And then we also have the Ozone Manager. Ozone Manager is the namespace manager. The namespace comprises of volume, buckets, and keys. Ozone Manager maintains a mapping from file or object to set of blocks where that file data or object data is present. A block is represented by a block ID. Block ID is a combination of container ID and local ID. Container ID represents the container where that block is stored. local ID is specific to the container. So Ozone Manager only keeps a working set in RAM. That is a great advantage with Ozone, because that is how Ozone is able to scale to billions of objects. Further, the container abstraction, as discussed, it reduces the number of entities which SCM has to manage or maintain. So that is also helping a lot in providing much better scale with Ozone. Further, Ozone also has a recon server. This is a reconciliation service. It is like FSCK in HDFS. This service is running in background. It is finding missing or corrupted files. It also has a UI. So admin or user can access the UI to find information regarding the cluster or any corrupted or missing files. There is a very clean separation of a block layer and namespace layer in Ozone. This is very helpful in better maintenance of the cluster. So now let's look at the write and read key workflow. For writing a key, client would issue a create key or put key call to Ozone Manager. Ozone Manager in turn makes a RPC call to SCM to allocate a block for the client. The block is related to a particular container, and every container is corresponds to a pipeline. So what is a pipeline? A pipeline is a set of data nodes where that container would be written. So once the block information is received by O1, it will pass that information to the client. Client will now communicate with the data nodes, and it can write its data as chunks in the set of data nodes provided. So this data write happens via raft consensus protocol. At the end, client would do a commit key operation. Once it has written all the data, it can do a commit key operation in Ozone Manager, and the key would be visible in the Ozone Manager namespace then. For reading a key, a client would make a get key call to Ozone Manager. Ozone Manager would return the key location infos. These key location infos are basically information regarding the blocks. So there is a set of blocks which that key is comprised of. So Ozone Manager would return the information regarding the blocks and the pipeline where that block is present, or the set of data nodes where that block is present. Client can then communicate to the set of data nodes for the corresponding block, and it can issue read requests to read the block data. So this is how write and read key workflow looks like for Ozone. So we can now look at the namespace and storage layer. The namespace comprises of volumes, buckets, and keys. Volumes are like user accounts in Azure, and buckets and keys are similar to what S3 provides. Ozone is a strongly consistent system. The strong consistency comes from raft consensus protocol. All the metadata updates or data updates in Ozone, data writes happen via raft consensus protocol. Further, the namespace can be accessed using Hadoop compatible file system API, Ozone file system, or the S3 protocol. The major big data applications can access Ozone using the Ozone file system, whereas the non-big data application can access Ozone using the S3 protocol. So now the storage layer. As we have seen, storage layer comprises of data nodes and SCM. Container is a very basic component of the storage layer. By default, a container is of size 5 GB. It contains a set of blocks. The container is replicated using raft consensus protocol. So all the block writes inside the container to all the data nodes which store that container happen via raft protocol. Every container has a unique container ID. Every block has can be represented using a combination of container ID and local ID. Local ID is specific to the container. So data nodes and SCM, data nodes manage the disk volumes in the physical host. The data nodes are take care of container creation. They decide which volume should the container be created in, and other container related operations are done by data node. Then we have the storage container manager. Storage container manager is more like a cluster manager in Ozone. It receives container reports from data nodes. It will make sure that the containers are sufficiently replicated. So now let's look at the structure of a storage container. So what does a container in Ozone look like? So container consists of data files or chunk files. These files comprise the block data. Then we have a RocksDB instance for storing the metadata related to blocks. So every block is a separate key in RocksDB, and the block, the value for that key would be information regarding which files, data files the block is present in, and other metadata like checksum or some other information regarding the blocks. So that was a brief introduction about the architecture of Ozone. So now we can dive a little deeper into how deletion or balancing of data across data nodes happen in Ozone. So in Ozone, deletion happens by a client. So client can make a delete key request to Ozone Manager. This is an order one operation. It's a namespace operation. So as soon as the this request succeeds, the key is no longer visible in Ozone Manager namespace. This is the namespace update, and then there is a data deletion which needs to happen. So the data deletion happens in background in Ozone. So once the key has been deleted in Ozone Manager, the Ozone Manager would move that key to a separate RocksDB table. So this table would store all the deleted keys in Ozone. And then there is a background key deletion service running in Ozone Manager. This service would periodically scan this table, fetch the list of deleted keys, and send it across to SCM. SCM would then have its own background service, which is communicating with data nodes, and it will send the blocks to be deleted to the data node. We'll look deeper into the design and how Ozone Manager, SCM, and data nodes end up deleting the data. So let's look at Ozone Manager and SCM communication. So as we discussed, Ozone Manager has the deleted keys in a deleted table. There is a background key deletion service. It will scan a configured number of keys every minute, or whatever the configured interval is. So after scanning those keys, it will send the list of blocks to be deleted to SCM. What SCM does now is it will create deletion transactions, and these transactions are list of blocks, which are all these blocks correspond to a specific container. We'll look deeper into how these transactions are created. So let's say Ozone Manager sends the following list of blocks to SCM. So we can see that the initial 4 blocks belong to container 1, and the last 3 blocks belong to container 2. So what SCM does is it segregates these blocks based on which container they belong to. So the first 4 blocks, there would be a new transaction created. And for the last 3 blocks, there is a different transaction. Every transaction has a corresponding transaction ID. This transaction ID is monotonically increasing. The transaction ID helps in giving consistency guarantees to SCM. So all the deletion happens with the transaction ID update, and SCM can make sure that the data nodes, the container transaction ID reported by the data nodes is consistent with the transaction ID stored by SCM. So now let's look at the SCM and data node communication. SCM has a background block deletion service. This service, so as we have seen, SCM would create transactions when it receives these blocks to be deleted from OM. This service would scan these transactions based on their transaction ID. So the first, it's a FIFO queue kind of service. So the transactions created earlier are processed earlier by SCM block deleting service. So once it will scan all these transactions, and since every transaction belongs to a specific container, that means these transaction would be sent to a set of data nodes, since every container is present in a set of data nodes. So what SCM block deleting service does is it will send these transactions to those data nodes containing the container. Once all the data nodes send an ACK to SCM, the block deleting service would delete the transaction from its proxDB table. Another thing which SCM block deleting service takes care of is that it makes sure that all the data nodes delete or process the transaction. So in case the replication factor is 3 and only 2 data nodes so far have ACKed the transaction, the deleting service would not delete the transaction. So data node, on receiving this transaction from SCM block deleting service, it will store this transaction in the container rocksDB. So we have seen earlier in the container structure, there is a rocksDB instance storing the metadata, metadata for the container log blocks. What data node does is all the transactions it is receiving for a container, it will store those transactions in the rocksDB for that container. And as soon as that DB update is done, data node would send an ACK to SCM that it has processed the transaction. The actual deletion of the blocks in the transaction happens in background by block deletion service. What this service does is it will read these transactions, fetch the blocks which need to be deleted, and it will issue file system delete request for these blocks. Okay. So let's now compare HDFS block deletion with Ozone. In HDFS, default heartbeat rate interval is 3 seconds, whereas in Ozone, the heartbeat interval is 30 seconds. By default, HDFS can delete around 20,000 blocks per minute. Ozone is also able to delete around 20,000 blocks per minute. So how Ozone is able to match the HDFS block deletion performance, provided that the heartbeat interval for Ozone is 10x larger than what it is for HDFS. So what HDFS does is the data node will send an ACK to name node only when the corresponding blocks have been deleted in the data node. That is until the underlying file system has actually deleted these blocks, the data node would not send an ACK to the name node. Whereas in Ozone, as we have seen, the data node does the deletion in 2 phases. Phase 1, it will just store the transactions in the container rocksDB. In the phase 2, it will delete or issue actual deletion for the blocks via the block deletion service. So this asynchronous deletion is a major factor for Ozone to be able to match HDFS performance. Every minute, SCM would scan 20,000 blocks to be deleted, and it will send these blocks to the corresponding data nodes. And these data nodes would ACK or send an ACK back to SCM in the next heartbeat. And in this way, SCM is able to delete around 20,000 blocks per minute. So what this does is it reduces the block deletion performance to a flow problem. So there are three components involved, right? Ozone Manager, SCM, and data node. So the initial flow is from Ozone Manager to SCM, and that is also configurable. There is a configurable limit on how many keys OM can send per minute to SCM. And then there is a configuration for SCM to control the number of blocks it is processing per minute. And based on these two configurations, the deletion speed can be adjusted for the entire cluster. The actual deletion of blocks or the metadata operations in the data node are further controlled in the data node. So there is a configuration on how many blocks is a data node supposed to delete per minute. So that is also configurable today. So that is how deletion works in Ozone. And now we can look at how balancing happens for across data nodes in an Ozone cluster. So why is balancing required? There is a chance that new data nodes are added in the cluster, or the data is deleted, and it may happen that the deleted data is more concentrated on some data nodes, leading to an imbalance in the amount of data stored in the data nodes. So in such a scenario, there is a need for a balancer service. In Ozone, the container balancer service is part of SCM. It will, so this is in contrast to what HDFS does. So what HDFS does is HDFS has a separate balancer daemon, which is running outside the name node. And the balancer daemon would have to make RPC calls to a name node in order to fetch utilization info or the blocks for a particular data node. So this would interfere with the other client processes or the other name node operations. And in a typical HDFS cluster, balancer can cause some performance degradation for the name node. Whereas in balancer, in an Ozone, the balancer is part of SCM, and so there are no separate RPCs involved. It can use the interfaces provided by the SCM components in order to do the balancing. Since the data nodes are heartbeating and they are providing utilization info every heartbeat to SCM, container balancer can use that same information for deciding the which data nodes and which containers need to be moved. So now let's look at how container balancer operates. In a typical container balancer operation, there are multiple iterations. In every iteration, container balancer will identify over and underutilized data nodes. It will identify source and target data nodes based on some selection criteria. And then it will identify which containers should be moved from source to target. This is also based on a selection criteria. We'll look further into these selection criteria in the next slide. And then once it has decided the source and target data nodes and the containers which need to be moved, it will issue move request to replication manager. So what this move request looks like, it contains a container ID, the source data node, and the target data node. And in return, replication manager returns a completable feature, which balancer can refer for knowing the status of move. So move was a new API which was added for balancer. So what does a replication manager typically do? A replication manager would have does all the replication work. That is, In case it finds out which all containers are under-replicated or over-replicated. For under-replicated containers, it will issue replication commands. And for over-replicated containers, it makes sure that the excess replicas are deleted. So for move, what a replication manager does is it will replicate the container to target data node. And then on successful replication, it will also issue delete container request to the source data node. Once both these operations are completed successfully, the replication manager would complete the future successfully, and then balancer can know that move is successful. So container balancer is a stateless service. It does not contain any information regarding data nodes, utilization infos, or the container infos. So it does not maintain any of this information. And that helps a lot in the iteration design. Every iteration is a new process or a new operation for balancer to identify the state of the cluster. And once it identifies the state, it will determine the overutilized, underutilized data nodes again and issue move requests accordingly. And then we have an interface-driven design. There is an interface which balancer requires to get the data node utilization info. It requires an interface to get the container and replica information for overutilized data nodes. So both these interfaces are already provided as part of a SIM node manager or other components. So some new interfaces were added for specifically for balancer. These were selection criteria or selection interface for to determine which containers should be balanced. Selection criteria for target data nodes to determine which target data nodes containers should be moved to. And then there is an interface to move the selected containers. So this interface-driven design is very useful in extending balancer to balance hot and cold data in the cluster. So all it needs is a hotness and coolness evaluation metric. And once that is done, balancer can move containers to make sure that the data or hot data is equally balanced or cold data is equally balanced in the cluster. Container balancer also provides limits, and it can be used to throttle the way moves are happening. So there are configurations to limit the maximum size, which is moving from target source data node and which is moving toward target data node. So this configuration is per iteration. Again, there is a configuration to limit the maximum size moved by balancer per iteration. And then there's also a configuration to limit the percentage of total data nodes involved in balancing. So a user can say that he or she wants only 30% of the total data nodes to be involved in balancing. There is also plan to add configuration for to limit the bandwidth for container move. So we don't want container move to occupy a lot of bandwidth or a network bandwidth or disk bandwidth in a data node. So there is that would also be added in the future. Container balancer is currently an under progress feature. Most of the work is done, but there are some pieces where work is still ongoing. There is also selection criteria for target data nodes or the containers. So it is important for container to obey placement policy after replication. What that means is the new set of data nodes where that container would be present after container move, they should obey the placement policy. So this placement policy can be something like all the data nodes should be in separate racks, right? So balancer needs to identify the target data nodes accordingly. So one obvious criteria is that target data node should not already contain the container being moved. Then user can also provide its own data node list for source or target data nodes. And priority of replication should always be greater than priority for balancing. So in case replication manager finds under-replicated containers, it should give more priority to these under-replicated containers rather than giving priority to these to the balancing of containers. There is also a selection criteria for containers. Containers should not be undergoing replication. That means it should not be undergoing either replication or deletion. It should not be under or over-replicated. It is better to move containers which are not following placement policy right now, so that a suitable target data node can be identified for these containers. And it would help the cluster overall to maintain a placement policy. It is better to move larger containers if possible. So that is also included in the selection criteria. And then user can also provide its own exclude and include list for containers. So that was all about balancing. One more thing about balancing is that the maximum size and some of the configurations which we discussed to limit the balancer move, they can also be used to identify how quickly the balancing would happen. So just by knowing that the maximum size container balancer can move per iteration, multiplied by number of iterations and the interval of these iterations would give us an idea about how fast or what is the balancing rate in the cluster. So in case of any queries or feedback, please reach out to me on my email, ljan@apache.org. Thank you.